Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
To welcome Roshana Groshandel. I asked Roshana to come by today at MSR since she was already at MSR, but that's why this talk was set up so quickly and without much announcements. But I'm happy to see, nevertheless, so many faces, and I think the topic is really exciting. As you all know, Microsoft wants to put more effort into architectural modeling, and of course, without considering reliability, that is actually of no real good. And so we'll hope to learn more about this topic from Roshana today. Thanks for coming by.
So actually, before going into the topic that this talk actually covers, I want to give a little overview of what I've been doing, the research summary that I've been involved at grad school. The topics really cover, our group is a software architecture research group, so everything is architectural in nature, but it kind of goes in various directions. Everybody picked a little piece here and there, and everybody worked together in a way on various pieces. So we deal with architecture-based software development. We do modeling and analysis of this specification. We have done a little bit of work on code generation and implementation infrastructures and frameworks and things like that. Some work on dependability analysis, and I'm presenting the one on reliability that is the topic of my dissertation. And as part of this whole process, we worked on adapting these various modeling and analysis techniques for various resource constraint and distributed domains on handheld devices and things like that. There has been, I guess the initial project that I was working on was an architectural evolution project, basically modeling and analysis of product families and combining configuration management and software architecture together. And finally, I have been an intern and then since then continuing working part-time at JPL in modeling data-intensive systems using a data grid framework. And I briefly talk about these various things. So the modeling and analysis really covers various modeling notations and architecture description languages and things like that. C2 saddle has been traditionally what has been done in our group. We have since kind of moved away, at least the students have moved away to various extensions and things like that to make it more generic and more applicable to various styles. We've done some state-based modeling using finite state machines and state charts and things like that. I have worked on modeling or considering modeling from various perspectives because you really need to have these various views onto a system. You can't just have one single specification to sufficiently describe your system. And it covers interfaces, static and dynamic behaviors and protocol. I briefly will talk about this in the context of the reliability model that I will talk about. And for architectural analysis, we have been doing topological constraint checking and type checking and conformance checking between these various models and deal with some theoretical issues in behavior subtyping and things like that. As for implementation and runtime issues, most of our work is on top of an architecture framework. There were various versions of it, whether it was a C2 framework from several years ago or the newer version, which is Prism, and C2.FW, which is another framework from UC Irvine, developed at UC Irvine. Again, adaptation of these various frameworks for distributed and resource-constrained devices. And then we have some code generation, basically skeleton code generation for based on the specification that we have. And these were done in the context of various projects, mainly.
What's
C2?
C2?
C2 is an architectural style that deals basically dictates, constraints how your components and connectors can be constructed to build system. This was initial work that my advisor did as a grad student. So we have kind of inherited all of his work, and we are building on top of it. And these works were done in the context of the two largest projects that we've had. One was a DARPA project, and we built a troops deployment system using these various techniques that we were advocating. This was done in collaboration with some Army labs. So this is not a real system, but it's at least done externally, not necessarily just by our group. It's not a complete toy application either. And also, we've used the architectural modeling and evolution work in the context of JPL's mission data system. JPL's Jet Propulsion Laboratory is one of NASA's lab in Southern California, in the context of the Scrover, which was an application built on top of the MDS framework. Evolution and data grid, I just put them on the same slide. They have nothing to do with each other, but just to save some space. So I talked to Wolfram about the architectural evolution work that we had done in May, which basically is a system model and an environment for managing the evolution of architecture. Instead of looking at a coarse-grained, just managing the evolution of your architectural artifact using a regular configuration management system like RCS or something, we actually have a system model that combines the CM and architectural concepts together and enables you to make perform useful analysis on these various versions of artifacts to see how they work together. Finally, the modeling data-intensive systems. This was, as I said, the internship work, which I was really hired to do dependability analysis on top of this OODT framework that they have, but it's just everything with government goes so slowly that I have to work there another 2 years to be able to actually run my work or models on it. We worked on building models, but we never got to actually measuring anything about those models. So now I'll talk about the actual topic of this talk, which is software reliability estimation during architectural design. I start by giving a typical software development scenario. It might be very different here at Microsoft, but I don't think it's very different. Typically, this is what happens. You have a designer or a set of designers that grab a set of requirements for building an application and try to come up with a blueprint for the system. These numbers are just hypothetical numbers. They're not too far from reality for a very small application, but it will take some time and some money to actually come up with that blueprint. And then programmers sit down and actually build based on that specification and build their system. And after certain amount of time has passed and they have spent a lot of money, they come up with a software, they build a software system. This is where actually test engineers and quality assurance people come into play, where they look at this, they run it, they test it, they try to find out whether it meets the dependability requirement that was initially requested. And do the dependability analysis on it. What happens is that the observation is that this is too late to actually look at the dependability aspects of the system so far at the testing stage when everything is already done. Most of the design decisions, most of the faults or problems that contribute to dependability of this or undependability of the system originate at the design stage. And this is too far off, too much money has been spent and too much time has been spent. And we really have to be able to have techniques that enable you to actually measure or quantify the reliability and dependability early on. And this is what this talk really is all about. So let me define what I mean by software reliability. It's really the probability that the system performs its intended functionality without failure. And usually software reliability techniques are aimed at reducing or eliminating failure of software system. What happens is that, as I said, they are usually complementary to the testing state. So people usually wait until they test the system, they run all kinds of tests, and then based on that, measure the reliability of the system. The question is, how can we build reliable software system, and how can we measure the reliability early on before the actual implementation is complete? So software architecture, so since I'm talking about software architecture and reliability, I'm just defining some of the terms of software architecture. It's really high-level abstractions that describe the structure, the behavior, and the constraints on a software system. They are coarse-grained building blocks such as components, units of computation, connectors, units of communication, and interfaces that connect these various components and connectors to one another. And they promote separation of concern and help reuse in the system. Obviously, architectural decisions that happen early on in the development process affect the dependability of the software system. And although there are various analysis and modeling early on, they typically lack quantification and measurement. The related work on this topic really spans across multiple research areas. It spans across reliability, which is a very much older field. Reliability engineering has been applied to hardware reliability and mechanical systems reliability and things like that, but they really don't necessarily address the software reliability too well, so they have to be adapted for it. And it also spans on architectural modeling, various architectural description languages, formal modeling notations, and things like that, behavioral and structural specification of the system, analysis for consistency and interoperability, and then the various views that I just talked about on modeling the system. Reliability techniques are, as I said, typically applied to the testing stage. They either consider the system as black box or white box. And the black box techniques, as the name says, they just run the system as a whole unit, monolithic unit, and measure, look at the failure behavior of the system and measure the reliability. And the white box techniques actually look at the structure of the system when they are considering the failure behavior of the system. So in a way, the common aspect is that both black, white, and white box approaches still require implementation and a running system, even though the white box approach considers some of the structural aspects of the system. So I went through various reliability techniques that were claiming to be architectural in nature and tried to classify them to see what are the various aspects of them. The main question is whether they operate on the code-based system or on the specification. And obviously, when I'm talking about architecture and I'm talking about not having implementation available, I'm really interested on the techniques that are applicable to the specification. The code-based approaches are divided to black box and white box, as I mentioned. The second aspect was architectural relevance. So what do I mean by architecture? These are really the main aspects of architecture that I'm interested in: components, connectors, interfaces, configurations, and architectural style. So a reliability model for software architecture really should consider all or most of these elements as a first-class citizen into it. The richness of the model was the next one, whether they are only modeling the interfaces, the signatures of these various components or connectors, whether they are looking at static behaviors such as pre and post conditions, whether they look at the dynamic behavior of component, which is exactly how the component goes about performing what it's supposed to be performing, and whether they consider protocols of interactions among various components and connectors in the system.
Question.
Sure.
Architectural style somehow seems out, not exactly out of place, seems a bit out of place. You know, components, connectors, so very obvious, clear things.
Yes.
What is architectural style? How do you...
Architectural style or patterns is how you actually compose these various components and connectors. So how the various constraints that are applied to how you are developing your system. So based on your domain, based on the type of application you're building, you might actually always, whether you're using a client and server architecture, whether you're using a pipe and filter, or these are architectural styles. So depending on the architectural style, you might be able to reason about the reliability of the system because it's demonstrating a particular architectural style. So in a way, architectural style takes components, connectors, interfaces, and configurations together and constrains them on how they are connected, how they are interacting, and things like that.
So it's not something like a taste of an architect?
No. No. It's really patterns that govern the composition of various elements. The one observation was that the interaction protocol models really, what is called interaction protocols in the literature either talks about the control flow or interaction among these various components. The control flow really says this component is being executed right now, and then the transfer of control gets transferred to another component, and then gets transferred to another component, and they build state machines based on this behavior. But the reality is that in a real system, you have various components that are really executing in parallel. So looking at the system as the control flow behavior is just simplifying it too much. You really should be looking at these various concurrent interaction between components and connectors. And finally, the last aspect is the technique that is used for estimating the reliability, whether they are looking at the reliability as one unit, the system as one unit, or they are having a compositional approach of first calculating the reliability of components and then putting it together compositionally to actually calculate the reliability of the system. And even the techniques that are out there that are compositional in nature, they usually assume we already know the reliability of components. Papers often start with this component has been purchased, and we have the specification sheet, and it tells us what the reliability of the component is. That's not how the world works right now, at least. So assumption-based versus estimation-based is what I said, whether they are assuming that they know the reliability of component ahead of time, or if they are actually estimating the reliability of components based on the data that they have. And the technique that my technique really covers these aspects. So it's based on a specification. I'm currently, at the moment, not considering architectural styles, but that's one of the extensions that I could build on top of this. I'm looking at interfaces, static behaviors, and dynamic behaviors, and interaction protocols, and I'm calculating the reliability of components first individually, and then putting them together to come up with the reliability of the system. So this is really this slide represents my technique at a high level. So these various four views of the system are really, I'll show an example of it, but they are typically what maybe not everybody models every single one of these four views, but it's really something that is needed to comprehensively model the system. And what's more important is the relationship between them, how they are, how is their conformance, whether they are compliant, whether they are violating one another. I put these four views together and define some of these rules for conformance analysis, and this whole framework is called the Quartet. And then architecture is really a combination of these various components and connectors together that have this type of model. They constitute the architecture of the system. And then I'm using Markov models, or more specifically hidden Markov models, to calculate the reliability of each component individually without considering its interaction with the rest of the system. And then this is called local reliability, or the component reliability. And then the whole thing is put together to come up with the global reliability, or the system reliability. And I forgot to mention that I'm using dynamic Bayesian networks to actually put this together to model the overall behavior of the system. So if you really think about this, what we are trying to do is to have this architectural specification of the system, to analyze, to run the analysis, and these analyses are typical analyses that are run, are used for reasoning about the architecture of the system. And then we want to measure properties such as reliability, or in this case, really functional reliability of the system. So reliability based on functional properties of the system, as opposed to reliability of the underlying network link, or the operating system, or the hardware-related issues. Sure.
Some problem. You say you take a component and you look at it as a Markov process. Now, in order for this to be Markovian, it should depend only on the current state.
Yes.
History is not important.
Yes.
But there is this interaction.
Mm-hmm.
So not everything depends on the current state. It depends on the environment.
I'll show an example of the state chart that is used to build the Markov model. It depends how, it really depends on your finite state machine. So a typical, let's say, UML state charts models states with a set of state variables. So we have a set of variables that are associated with each state. And at each level, at each stage, it really does demonstrate the Markov property, because the next step in the process is irrelevant on how I arrived at this current state of the system. I'm at the current state. If something happens, I might go to another state, or I might go to a third state, or I might stay here.
So the interaction is between the states, right?
Yes, yes. So the elements of the approach, the architectural modeling element, there is the architectural modeling element, there is the analysis for various consistency and conformance, there is the quantification of defects. So once we actually do analyze the system, we might come up with a set of errors or defects, and they somehow are affecting what we call the reliability of the system. And the question is how important they are. If there is, for instance, an interface mismatch between two components, those two components cannot communicate, period. Whereas if there is a protocol mismatch between them, there is some conditions under which there may be a problem with the communication of the system. So it's not always that the two are, cannot communicate with one another. And basically, understanding and deciding how they are affecting your system, how to quantify this, is something that is very specific to the domain and application that is used. So I'm not really advocating any particular defect quantification technique. I'm just giving a generic thing that has to be instantiated, and I will talk about it exactly what I mean by it. But it's that's not really, I'm not claiming that I know how to quantify all the defects that are out there. And then finally, the reliability estimation, which is hidden Markov models and dynamic Bayesian network. I'll talk about them. I already talked about these interface static and dynamic behavior and protocols. So these are just a definition. Interfaces are signatures. Static behaviors are snapshot view of the system, pre and post conditions. Dynamic behaviors is how the system arrives at these various things, usually modeled using some state-based notation. And finally, interaction protocols, which is the external view of the component. So dynamic behavior is the internal view. The protocol is the external view. And this is the grammar that I have defined for my purpose. But this is in a way, it looks like a grammar. But this is typical thing that is, again, out there. Anything like UML or other ADLs or modeling notations could be mapped to this. So there is nothing spectacular about this particular notation. This is an example of it. So the diagram on the top left is really like a cruise control component. It has a set of required and provided interfaces. On the left, bottom left, you see the interfaces. In this case, we are just talking about the provided interface. There are static behaviors, which is really the operations pre and post conditions. And then there's the dynamic behaviors, which talks about the behavior of the component itself, how it does its functionality, and the interaction protocol is the external view for interaction with the rest of the system. The important thing is how they relate to one another, whether these various four views are compliant. So if different people are looking at the system, they may be interested in one particular view of the system. Somebody may be just interested in the interfaces, whereas somebody else may be interested in protocols and things like that. The important thing is to make sure that these four views are compliant with one another. And I actually have a definition of what it means for these various views to be compliant with one another. Once we do analysis to make sure that there is compliance and conformance among these models, we come up with a set of architectural defects. And as I said, different defects affect the reliability of the system differently. And the cost of mitigating those defects varies. So domain-specific factors are important when we are actually quantifying these defects. And this was a defect quantification. For quantifying these defects, we have to first classify the defects to see what type of defects are out there, and then try to put a number into it. This defect classification was something that came up as a result of collaboration with another university, Carnegie Mellon University, in the context of a NASA high dependability computing project. So we were analyzing the same system separately, independently from various perspectives, and then we realized that our approaches are somewhat complementary, and this was the type of classification that we came up with, which covered all the architectural issues that we were interested in. I'm not going to get into details of defining what these are, but basically either the defects are topological in nature or behavioral, and then there's various type of topological or behavior errors that can occur. Finally, the cost framework is what puts these things together. So you analyze your system, you come up with a set of defects, you classify your defects based on this classification. Again, there is nothing spectacular about this classification. In another domain, in another application, in an organization, you may have your own defect classification technique. My technique doesn't depend on this particular classification. You can plug in another one. As long as you have a way of quantifying and coming up with a value for this defect that you're discovering, that's all we need. The cost framework, the same thing with the cost framework. So once you classify the defect, we want to quantify it, to put a number into it. And this might be domain specific. So all I'm doing is that I'm saying a set of factors are related for your particular domain, for your particular organization. For instance, the severity of a defect might be important to you. Or, and you define what the severity is. I'm not doing it. But I will show an example that, that uses this. And also frequency of occurrence. So if you have an error that only happens once, it might be more or less important to you than if you have an error that every time that you click on a button, it happens. So that type of factors have to be considered when you are quantifying this. So this is a sample instantiation. I'm defining two factors, severity and the effort that is needed to mitigate that defect. And I'm defining what is the severity of, based on that classification that you saw, I'm defining what is the severity of that particular defect type, and what is the effort that is needed for mitigating that particular defect type. And I'm just putting it together, so this is just a way to come up with a number based on the errors that I'm getting. Some of, so if you look at the chart on the left-hand side, some of the errors are low severity, high effort, high severity, low effort, and all these various combinations. And I come up with some nominal value for each of these factors. And based on that, measure a number, which eventually, in this diagram, tells us that at each of these various steps, at stop state, manual state, or cruise state, this was a cruise control component that I just talked about, you come up with one of these values. So in this case, I'm calculating the value for the manual state, which basically says at that state there is this much chance that an error might occur. That's what this value translates to.
In this example, can you give examples of defect? What is D-gap, D-break? What kind of things?
Okay, so as I said, I'm defining two factors, severity and effort. And I'm defining nominal values based on my understanding of this particular domain, that this was a robot that we were building. Based on that, I'm saying that what the nominal value for these things are. And basically the distance between the measured value, so when I'm looking at, I have a signature error here and a static behavior error. There are two types.
I understand. If you have defect, you classify them. I understand the rest of it.
Okay.
How do we find defect?
How do I find it?
Yeah, what is a defect?
We have,
so in this particular example of the cruise, can you show what kind of defects are there?
So I think we found a signature mismatch here. So here there was, I don't remember exactly what was the defect that this came out of, but for instance, a signature error means that there is a signature here, there is an interface here that does not exist in your interface specification, for instance. So there is a mismatch between, there is a problem with what you have in this diagram and what interfaces you have initially specified for your component. And the static behavior error is, for instance, as I showed you these four various views. So the conformance between these four views is what we analyze. And if there is an error, that constitutes a defect. So in the static behavior case, for instance, there has to be a compliance between the pre and post conditions on your system and the guards on the transitions. They're not shown in here just for space purposes, but there has to be a relationship between them. Thank you.
It's a critic can say, instead of quantifying defects, why not to correct them?
Sometimes you can correct them, yes.
I think this work is not about finding the defects, but suppose we have found the defects with testing technology or any other technology, you want to know what is the impact of the overall defects on the overall architecture.
And sometimes you cannot fix that defect. Sometimes you are using components that are off-the-shelf components, or you are using components that you don't have access to fixing they're specific. You really don't have control over them. So some of those defects you definitely can fix, but there are defects. So for instance, when we were building this was built on top of Mission Data System framework, which was a framework that we didn't have access to its code. We only had access to its binary. It had more problems. People who were not US citizens, you could not even look at the binary. It was just, a whole big mess. So when we would come up with these mismatches sometimes, we couldn't, there was no way that we could fix them. We just had to live with them. And obviously in the implementation level, somebody would get around them, test it and figure out a way around them. But they existed at the design stage. So how do we calculate the component reliability? If you look here, I talked about the architectural models that we have. So we run analysis on it, come up with a set of defects, run it through the quantification step, and come up with that state reliability value. Then the problem, usually there are other techniques that just use a similar type of state machine-based approach to modeling the behavior of the component, and then they just assume that there is Markov property there and calculate the probability of reaching a final state in that model. The problem is that because we don't have actual implementation of the system, we don't know the operation profile of the system, we don't know how it's going to be used, we don't really know these various probability of various transitions getting activated. So in a way, and then if you look at the trace of the system, if you look at the various interfaces that are getting executed, we don't necessarily know, there is not a correspondence between the transitions and the states. So in that diagram, in the dynamic behavior diagram, if I'm seeing that there is a gas transition followed by another gas and then pushing on a brake, but I can't exactly say, okay, here I was at this state and now I'm at this other state and now I'm moving to a third state. There is not a single correspondence between them. So as a result, really a hidden Markov model is a more appropriate formalism for coming up with the reliability as opposed to a regular Markov model, because there are parameters that we don't know. And our model has to account for these uncertainties that are in the system. So there is a hidden Markov model that basically from the architectural model, from the dynamic behavior model, we are extracting another state chart and then run it into this Baum-Welch algorithm, takes some other parameters such as initial transition probabilities, which can be either random or they can be instantiated by the domain expert. And then as a result, we come up with these transition probabilities, which are really the frequency that various errors might occur. So this is just to accommodate for the fact that we don't have a running system, we don't have simulation of it, we don't really know much information about how many times various interfaces get executed and things like that.
Let me say just for my sake of understanding.
Sure.
By hidden Markov model, you mean there is a real Markov model, but you know only part of the state. And
Yes.
So you follow only a projection of a state.
In this particular case, we actually do know the states because we have the behavioral model. So we know what the states are. It's just that if I'm looking at the running system, if I'm simulating the system, I can't say, okay, this is the trace of various interfaces that are getting executed. So this is, I went from state 1 to state 2 to state 3. That I wouldn't know because...
So you're forced to look only, not on every state, but on once a while, right?
In a way, yes. And also the other problem that we are going with hidden Markov model is that if we wanted to go with a Markov model, we had to know the probability of each transitions, right? So we assume that we know the transition. So what is a Markov model? It's a state chart that is decorated with transition probabilities. Now, in this particular case, we don't know what the transition probabilities are. If I was running this based on an actual implemented system, then I could run the system implementation, log various events that are happening in the system, and have these frequencies of occurrence which constitute my probabilities or frequencies. I don't have that either. So we can't really use a regular Markov model because we don't know what those numbers are, the probability numbers are. Whereas if we use a hidden Markov model, the algorithm actually, based on some initial values that can be either random or can be assigned by the domain expert, can actually go and calculate the actual reliability probability values on the transitions. So that is the main reason that we went with hidden Markov model. Okay. So given these inputs, so inputs from the architectural model and these initial transition probabilities, the iterative process comes up with the actual transition probabilities on the system, and also with the component reliability at the end. So the reliability model, this was the process that actually is taken, but it's built based on top of the dynamic behavior model. It assumes the Markov property. The transition probabilities may be unknown. These are just a recap of what I was just saying. The complex behavior of the system results in a lack of a correspondence between states and events. And also we have these event-action interactions. So if you looked at the dynamic behavior model on the transitions, we have event/actions. So an event in one component may cause an event in another component eventually. And that's something that the typical hidden Markov model had to get extended for to actually accommodate for these actions. The typical hidden Markov model only looks at the one parameter on the transitions, basically. So this is what we call the augmented hidden Markov model. I'm not going to get into details of these parameters, but basically these are the parameters of the hidden Markov model, defining the states and events and the transition probabilities and things like that. These are some of the properties of, just the typical properties of a hidden Markov model that also are applied to our work, and how the Baum-Welch algorithm can be applied to this. In this particular example, again, cruise control example, there are transitions added to the original dynamic behavior model to accommodate for uncertainties that are associated with errors. So, for instance, you are expecting. So that diagram really models the desired behavior of the system, but that may not happen. How many times you have a bug that you push something and something is supposed to happen and doesn't happen, or something is supposed to happen and something else happens. What that means is that when, for instance, you are expected to go from stop to manual when gas happens, there is a chance that you will just stop and stall where you were, or you might go to a different state by mistake. So this extension really models those type of uncertainties. This is the initial transition probability table. That is, again, something that the domain expert can come up with, or in the worst case scenario, we can actually randomize it. And we have some evaluation that shows when each of those approaches are acceptable. And then once we run the Baum-Welch algorithm, this expectation maximization algorithm, it actually recalculates that initial transition probability matrix. And then the reliability is really calculated by adding two states into the diagram that we have: the correct termination of the component and the failure termination. And that really means that if you are in a final state, there is basically. We came up with these reliability numbers that we calculated before. If you are at the final state, that means that you are correctly terminated. The component has correctly terminated. If you are at the non-terminal state, that means that there is a chance, whatever the reliability of that state is, there is a chance 1 minus that reliability that you would go to a failure state, basically. So we extend the model by this, like this, and basically this is an adaptation of an existing reliability model that calculates the probability of reaching a state after n steps. There are some more math formulas and examples of it. I'm just not going to
Sorry to torture you, but if you're on design stage, you have a design, there are no experts which can give you initial probabilities.
Whoever has designed the system has some sort of an expectation. So if I'm designing a cruise control component, I know that, okay, this is probably happens. This is when I come up with that diagram, pretty much I know what are the chances of various things happening. This is not exact science, and the whole approach does not depend on exact values of those things. So if you have a guess of what really are those probabilities, that's great. If you don't, still the technique is going to work. But if you have an initial guess, it will help to actually come up with more accurate values.
Also, you speak about final state, but many systems don't have any final state. They run forever.
So that could be a symbolic state in a way. So either you will define the reliability in terms of we are trying to measure the reliability of the system component, let's say, in terms of I want to know whether this cruise control component works after 10,000 times that the button was pushed on it. That way you can define a symbolic final state for the system. So yes, many systems are just long running, but you can either define this final state in terms of a time period, so that you want to see after 10,000 times steps interval whether you are reaching a final. Yes, it could move. So it depends on how you are defining your reliability. So this is just example of how the component reliability was estimated. And again, there is, I'm not really talking about reliability in terms of, okay, the greatest thing for evaluating this work would be if we had a running system and we had a design that was built, that the running system was built based on that design, and then you would run this reliability model on the design, and then run the reliability on the implementation and compare the values. But that, we are I think long away from reaching that point where we have an actual consistent implementation and architecture that we can reason about like this. So there is still a long way to be able to validate it like that. But at least we have some sort of a measurement of how the system is designed. The global reliability was a little more tricky than the local reliability in the sense that now we have these various components that, as I said, are running in parallel. So there is a lot of problem with the scalability, with putting these together, with even understanding how the interactions happens. So if I wanted to have, let's say I have 5 components, that means that I have 5 concurrent state machines running in parallel. If I want to build a flat state machine out of these 2, that's not a very scalable approach. At some point I have to stop and look at it differently. So basically, the other thing is to be able to model the interaction between various components. So when a component, let's say we have a user interface component on the car that when you push a button really activates something in the cruise control component. So in a way that event action pairs is what is used to actually model this relationship between various components. So an event causes an action, and that action may be an event in another component that gets triggered at the same time because these are all concurrent running. So what is the best way to actually model that? Dynamic Bayesian network or belief networks are actually can be used adequately to address that. This is the architecture view of these various components that are running in parallel. So we have components, we have connectors, and there are state machines associated. So the architecture of the whole system is comprised of these various concurrent state machines. And this is an example of it for the cruise control example again. So we have a cruise control component, we have a hardware proxy component, and we have a UI component. And then the UI component, you push on a button, it causes, for instance, the gas to get activated. That in turn causes this transition to get activated. This is how the actual interaction between the various components happens. And again, this is another view of it. So we have the 3 components. We have these various states in those components. And this is what happens. We start at the idle state or the initial state of all of these models. Something gets activated here, which causes a change of state to this other one. And that, in turn, causes a change of state in other components. So now we are really looking at how the interaction between various components are happening. And again, another transition gets activated here, which causes change of state, or in this case, not remaining in the current state in another component and things like that. So now this is the flattened version of that thing. So you have a series of states here, a series of states here, a series of states here, and changes in triggering of something in here will cause a change of state in the second component, and so on and so forth. This is really the only part of the work that is left to be done in terms of evaluating this part. Yes, sir.
If I understand correctly, when you're talking about those state machines specific for the components in isolation, you had those transitions that represented, from what I understand, failures in the components. They deviate from what is expected from them. And I don't see that sort of thing modeled there. Is it modeled there during the interaction? I mean, if one of the components there fails, it does something unexpected, that will probably interfere, will probably affect the components with which the failing components interact. I don't know if you're still going to talk
I haven't
about
looked at it. No, I haven't looked at it. And again, this part is the least mature part of my work. So I haven't, for the rest of it, I have a tool that is running and I can measure and things like that. For this one, it's still ongoing. It's not complete yet. But that's not something I looked at because that already makes, even though it's something that could be accounted for, I actually haven't thought of necessarily that I want to put it out or put it back in here. The reason for it is that it just makes it so complex that might be computationally impossible because we are already, looking at, if previously I had one component to look at and I was looking at its failure behavior, now I have, a ton of them, a bunch more. So it will make it computationally more invasive, but intensive, but I don't necessarily think that it's impossible. So you can just add those transitions. It just makes it very complex, and I don't know if the algorithm will be able to handle calculation of it. But that's definitely something. So another way to look at that failure behavior is really to build a separate model for failures. So this is the desired behavior of the system. You can also build a failure model of the system and the things that could cause failures.
What is the dynamic part in the dynamic Bayesian network? Is it belief revision?
Belief revision.
You mentioned belief.
Belief networks. The dynamic part, no, it's just there are two names for it. So dynamic Bayesian networks and belief networks are the same thing. It's used extensively in AI, but they use various terms for it. But it basically, the dynamic part, so if the dynamic part really is about the interaction between these various levels. So if it was a single one, it would be like a Markov model type of a thing, if we were looking at just this one. But because we are looking at these interactions, then it makes it dynamic.
That's all.
Yes. So this is basically how it gets calculated. We have the set of states that come from the Quartet model. We have interactions among these various states, again coming from the Quartet modeling. And then we have probability of various interactions that come from the component reliability estimation step that we just performed. And the goal is to calculate the system reliability as a probability of reaching a final state or passing a certain amount of time to basically calculate the final state. And then dynamic Bayesian, we basically know the structure and we have full observability of the system. That means that we know the transition probabilities this time, so it's not hidden in that sense. And it becomes a case of maximum likelihood estimation algorithm for solving it. So with regard to evaluation, as I said, I have done evaluation in the context of component reliability estimation, but not at the global level yet. There are really several things to look at. One is uncertainty analysis. The whole premise was that this can be done applied to the early stages of development when we don't have implementation and we don't know the operation profile of the system. So, and there are issues associated with incorrect behavior of the system. Whether this model can actually accommodate for this various uncertainties is important. And also, traditionally with Markov-based modeling, there are sensitivity analysis. Now, because we have the sensitivity analysis combined with defect quantification, we can actually reason about the importance of defect in the sense that, okay, we have these various components, these are their reliability, and it might be more important to fix a component with a higher reliability than the other one. So we know exactly how components are affecting the system reliability. So we would know which component is more critical to be fixed than the other components in the system. And then I'll talk briefly about complexity and scalability of the approach. So with regard to uncertainty analysis, how important is it to estimate these initial transition probabilities that we just talked about, or can they be random? Basically, how about slight changes? Like if the domain expert is coming with these ITP values, what if they make a mistake and those values are not exactly accurate? And so we designed a three-phase experiment that first we randomly initialized components probabilities. Then we did an intelligent initialization by the domain expert. And then finally, we did some noise introduction to see how it handles various ITP values. I'm not going to get into these various numbers, but basically the results showed that initial instantiation is very important when we have A very simple component. So if you have a component that is really, its behavior is simple, then you really need to, so there are a lot of, let's say, transitions that their probability is 0. They may not happen, or they have very low probability of happening. Then it's important to actually know that those are, initialize them to zeros or very small values. Whereas if you have a complex component that its behavior is very complex, then the precise initialization is not as important. And the data that I had in the previous diagram actually backs this up, and I have more discussion of it in the paper if somebody is interested. And this one was for the noise introduction. So the left-hand side and the right-hand side showed the various reliability estimation with introduction of this much noise. So the ITP values were changed by this amount. And if you see here, we are talking about like a 57%, I don't know, reliability, and here we are talking about 58% reliability. So the difference was not really that much. So it handles various changes or introduction of noise pretty well as well. These are not my contribution. These are the Baum-Welch algorithm contribution. I'm just using it.
The previous issue, would it be possible to show that evaluations are continuous in the initial distribution? That would show, mathematically would express insensitivity. So if you change a little bit initially, then the whole evaluation changes slightly.
I haven't looked at it, but the reason I haven't looked at it is that I'm using the Baum-Welch algorithm. I'm sure there's a ton of works on it that actually shows these type of things, because it's a property of the algorithm that handles uncertainties and things like that. I'm just putting it into perspective in terms of reliability. But I haven't looked at it from a proof perspective, basically, mathematical proof perspective, whether it's doable or not. As for sensitivity analysis, as I said, the Markov-based sensitivity analysis plus the cost framework help us identify critical states when we are dealing with component reliability, and identify the critical components when we are dealing with system reliability. And the result is that we can have a cost-effective approach to mitigating defects. Complexity and scalability, I haven't really focused too much on this. I just had a simple look at what was going on. So the typical Baum-Welch algorithm really, this is the complexity of it, which deals with the factors in the number of states, the number of events, and the length of the training data that is given to the algorithm. In our case, we are really adding one parameter to it, which is the number of actions. So we had these event action pairs. So this also gets added to it. The one thing that we can be happy about is that because we are dealing with hierarchical composition, we can help the complexity by just looking at various stages of hierarchy. And the scalability of the approach is also bound to scalability of the underlying formulas, and the state charts and things like that all suffer from this problem. So I haven't really looked at optimizing the approach. I haven't looked at, in a way, it's more theoretical at this stage. As for future directions, there are many various things that I can take this work to. So, for instance, the effect of architectural styles and patterns on reliability, that's something that we could look at. We could use approximation algorithms and fix some of the known parameters about the system that we know to actually reduce the complexity of the problem and help the scalability. Extensions to model the firmware properties, such as the operating system, underlying operating system, and network structures and things like that. Applying this to the OODT group that I was working with, Data Grid, is something that is still ongoing. If I end up working at JPL, continuing after my finishing up, that would be something that I will be working on. Applying the dependability analysis to other domain-specific problems, because that will help reduce the complexity of the problem as well. And also extending this dependability analysis to other, extending from reliability to also security and availability and other dependability aspects of the system. The relationship between improving the reliability and basically decreasing the performance of the system. So there is a relationship over there that can be looked up. And extension, so our modeling part, we have dealt extensively with modeling, analyzing product lines, but we haven't really extended this work, the dependability analysis, to product lines. And then support for architecture to implementation refinement. As I said, we had some code generation and things like that, but they kind of have stopped a few years ago and could be something that I would be interested in working on. And also some extensions to type theories for dynamic behavior models and protocols, so subtyping and things like that for state machines and protocols and things like that. And that's basically, this is the collaboration I already talked about and some list of publications. That's conclude my talk.
Okay, thanks a lot.
Thank you.
Are there any questions? Okay, we have so many questions. I think we should probably stop here. And Roshana is here, I don't know, for another hour and then stays in this yellow area. So if there's more questions, we can.
Yes.
Okay, thanks a lot.